Welcome to the Deep Dive, presented by Knowledge Flow. Today we're not just revving up, we're launching into a deep exploration of the very heart of what makes our vehicles move, interact with the world, and ultimately get us from point A to point B.
It really is a fascinating journey, isn't it? We're diving into automobile engineering, and it's a field that, it profoundly touches nearly every aspect of our daily lives, often without us even realizing the intricate dance happening beneath us.
Exactly.
We're going to pull apart the fundamental systems today, from how an engine first sparks to life, right up to how a vehicle safely, reliably comes to a stop.
That's right. Our mission today is to demystify the intricate ballet of components that allow us to transport goods and passengers. We want to understand the why behind these ingenious designs and, frankly, truly appreciate the sheer genius packed into these self-propelled machines we rely on every single day. So let's begin our exploration. Let's unpack this. Let's start right at the beginning, the absolute basics. When we say automobile, what exactly are we talking about? It's much more than just a fancy word for a car, isn't it?
You're absolutely right there. An automobile is fundamentally defined as a self-propelled ground vehicle. The key element is self-propelled, meaning it carries its own power source.
Right, its own engine, basically.
Exactly. Historically, and still predominantly, this power comes from an internal combustion engine, though, as you know, that's rapidly evolving now with electric and hybrid tech.
Sure.
Its primary purpose is for transporting goods and passengers, and critically, it's designed to move in any direction, whether that's on a paved road or even off-road terrain. It's a very broad definition, really.
So it covers a huge range.
Oh, absolutely. It covers an incredibly vast array of machines, everything from the smallest scooters zipping around cities to the largest multi-axle trucks you see hauling cargo across continents. It's truly a universal term for mobile mechanical transport.
Okay, so how does this self-propulsion actually kick off? We know we turn a key or press a button, but what's the sequence of events happening under the hood, leading to that initial burst of life?
Okay, so it all begins with cranking the engine. In most four-wheelers, like your standard car or a truck, you'll typically use an ignition switch to send that initial electrical signal.
Yep, turn the key.
Right, or push the button these days. For two-wheelers, you might have that familiar kickstart option alongside, or sometimes even instead of an ignition switch.
The kickstart. Good old days.
What cranking does, essentially, is initiate the piston's first downward movement inside the cylinder. As that piston moves down, it creates a really crucial vacuum.
Okay, a vacuum.
And this vacuum is what causes the surrounding air to rush in. First, it passes through an air cleaner to remove impurities. You can imagine trying to run an engine on dusty air. It wouldn't last long.
No, definitely not.
And then, after cleaning, that air makes its way to the carburetor.
And the carburetor. Now, for many of our listeners, that might seem like a bit of a relic now, right? Largely replaced by modern fuel injection. But can you quickly clarify why it was such a crucial component in its time? And maybe touch on the fundamental challenge it aimed to solve that fuel injection later refined.
That's a great point, because the carburetor was truly ingenious for its era. Its primary challenge, its main job, was to take liquid fuel petrol, usually, and transform it into a fine combustible vapor.
Atomize it.
Exactly, atomize it. Then it had to meticulously mix that vapor with the incoming air in really precise proportions. You see, you can't just dump raw liquid fuel into an engine cylinder. It won't burn properly. It needs to be atomized and perfectly blended for efficient combustion.
Got it.
This precisely calibrated fuel-air mixture then enters the cylinder through inlet valves that open at a preset timing. This ensures the right amount is delivered at exactly the opportune moment to maximize power.
Timing is everything.
Absolutely. Then, and only then, does the ignition system produce that tiny yet incredibly powerful spark, also at a carefully preset time. That's the moment combustion ignites, unleashing a powerful mini-explosion. And that explosion is the very first step in generating the vehicle's motion.
And modern fuel injection.
Well, modern fuel injection still solves the same fundamental problem, but it does it with electronic precision rather than purely mechanical means. This offers much greater efficiency and control over the fuel-air mixture under all sorts of conditions.
Okay, so combustion happens, the piston is pushed down forcefully, and then what? How does that violent, linear push of a piston translate into the smooth forward motion of a vehicle rolling down the road?
Right, this is where the core mechanical ingenuity really lies. That rapid expansion of the burnt fuel ignited by the spark pushes the piston forcefully down inside the cylinder. But like you said, a vehicle doesn't move up and down, it needs to move forward. So a very clever component, known generally as a slider crank mechanism, the connecting rod and crankshaft assembly, takes that reciprocating motion, that powerful up and down movement of the piston, and ingeniously converts it into a continuous rotary or spinning motion.
Ah, like bicycle pedals.
That's a perfect analogy. Think of it exactly like the pedals on a bicycle. Your legs move up and down, a reciprocating motion, but that gets converted into the continuous circular motion of the chainring and ultimately the wheels.
Okay.
Similarly, in the engine, this mechanism translates that explosive linear push of the piston into the smooth spinning motion of the crankshaft. And that crankshaft's rotation is what we ultimately need to turn the wheels and propel the vehicle forward.
And that power doesn't just jump straight from the crankshaft to the wheels, does it?
Yeah.
It sounds like there's a whole chain reaction, a careful sequence of events to get that power precisely where it needs to be, and importantly in the right way.
Oh, absolutely.
I can only imagine what a rough, inefficient mess it would be if any part of that mechanical dance wasn't perfectly smooth. What are some of the immediate consequences if, say, the clutch isn't precisely engaged?
You've hit on a critical point there. Smoothness is key.
Yeah.
Indeed, the rotating crankshaft first sends its mechanical energy to the gearbox. Now, this connection is managed through the clutch.
Right.
And to your point, if that clutch isn't precisely engaged or if it's engaged too abruptly, you'd get jarring lurches, excessive wear and tear on all the transmission components, and you could even stall the engine.
Yeah, we've all been there learning to drive manual.
Exactly. The clutch allows for that temporary disengagement, vital for changing gears or stopping, and then that smooth, gradual re-engagement, protecting the entire system.
Okay, so after the clutch.
From the clutch, power goes into the gearbox. The gearbox is where the vehicle's speed and torque are regulated for different driving conditions. Low gears for power, high gears for speed.
Makes sense.
From the gearbox, the power then goes to the propeller shaft, especially in rear-wheel drive cars. This shaft then transfers that rotary motion to a differential gear system.
And the differential is crucial.
Absolutely crucial, particularly for turning. It allows the drive wheels on either side to turn at slightly different speeds when you go around a corner. Without it, the wheels would scrub and handling would be terrible.
I see.
The rear axles of the vehicle are directly connected to this differential, sending the power out to the rear tires, causing them to roll and propel the vehicle forward. The front wheels then just follow suit, and the steering system, of course, allows you to control the direction of the entire vehicle. It truly is a delicate, precise mechanical dance from start to finish.
Okay. When we talk about cars, there's so many ways we describe them, from the model year to the color. But what are the universal specifications used in automobile engineering? The terms that truly define a vehicle from a design and operational perspective.
Right. Engineers have a specific language for this, a set of key factors they use to specify any automobile precisely. First, there's type. This is pretty straightforward. Is it a two-wheeler, like a scooter or motorcycle? Or is it a four or more wheeler, such as a car, truck, or even a bus?
See all that.
Then we have capacity, and this is actually twofold. It details the seating capacity for people. Is it a two-seater, a four-seater, a six-seater, and so on? And also the luggage or cargo capacity, which is often specified in tons for commercial vehicles, like a 1-ton pickup or a 3-ton truck.
Okay, and make and model are usually what people focus on when buying a car.
Yeah.
Right. But they have specific engineering meanings, too, going beyond just branding.
Absolutely, they do. The make is the name allotted to the vehicle by the manufacturer, often followed by some designation for the engine's power unit, indicating something like the number of cylinders, or maybe its horsepower. Think Ford F-150 V8 or Honda Civic 1.5T. This tells engineers about the fundamental design family and the potential performance characteristics. The model then indicates the specific year of manufacture along with the distinct code number provided by the manufacturer. This allows for precise identification of a vehicle's particular iteration because subtle design changes can occur year to year, even within the same overall make and model line.
And finally, drive.
Yes, drive is crucial. It specifies, first, if the steering wheel is fitted on the left or right-hand side, a critical ergonomic factor depending on the country's road rules. And perhaps more importantly from an engineering standpoint, it indicates how many wheels are connected to the engine shaft. This determines if it's a two-wheel drive or a four-wheel drive vehicle.
And that affects handling.
Massively. It directly impacts traction, handling stability, fuel efficiency, and ultimately, what kind of terrain or conditions the vehicle is best suited for. Two-wheel drive, four-wheel drive, big difference.
It's mind-boggling when you consider the sheer scale. I think I read somewhere there are over 500 million automobiles globally, maybe even more now. And what's truly fascinating is that we can't just classify them by one single criterion. It's a remarkably multidimensional system, isn't it? What are the primary ways engineers break down this vast world of vehicles?
You're right, it's a colossal number, and that diversity means we need multiple lenses, multiple ways to categorize them to really understand the landscape. We can start, perhaps most simply, by number of wheels.
Okay.
You've got two-wheelers like motorcycles and scooters, typically light and agile. Three-wheelers, including things like tempos and auto rickshaws, often designed for specific urban transport or utility roles.
Right, like in some cities.
Exactly. Then four-wheelers, which encompass the vast majority of personal cars, Jeeps, SUVs, and minibuses. Six-wheelers, such as larger buses and many trucks built for heavier loads. And then you get into eight or more wheelers, which are primarily used as heavy transporting vehicles like specialized freight carriers or articulated lorries.
Okay, what else?
Another rapidly evolving and incredibly important classification now is by energy consumption. This covers the traditional internal combustion engine-driven vehicles, petrol and diesel, which are still dominant globally.
What, changing fast?
Changing very fast. It also includes vehicles driven by historically steam engines, which is fascinating.
Wow, steam.
Still not really in common use, but part of the history. Also gas turbines, which you find in some niche high-performance applications, and then the big modern ones. Electric power, solar power, battery power, hydrogen propulsion, and increasingly hybrid-powered vehicles, which cleverly combine two or more power sources, usually petrol and electric, for efficiency or extended range. This category is where we see immense innovation right now, driven by environmental concerns and the search for efficiency.
Makes sense. What about their job?
Good point. We categorize them by purpose. You go from single-user vehicles like scooters and bikes, designed for individual mobility, maybe commuting. Then you have family vehicles like cars or Jeeps or SUVs, tailored for passenger comfort, safety, and versatility. We also have large transportation vehicles such as buses and trucks, optimized specifically for hauling lots of people or large amounts of cargo. And then specialized agricultural vehicles like tractors, built for heavy-duty farm work. Each purpose dictates very specific design priorities.
And how much they carry?
Yes, by load carrying capacity. This gives us lightweight, medium weight, heavyweight, and extra heavyweight motor vehicles. This isn't just about the payload number. It dictates the required robustness of their chassis, suspension, braking systems, engine power, everything.
Okay, and fuel type is still relevant?
Definitely. By fuel used. Petrol vehicles, diesel vehicles, dual fuel vehicles, which can run on more than one fuel type, and gas vehicles, like CNG or LPG. Each has different cost implications, efficiency ratings, and emissions profiles that really impact their suitability for different markets and uses.
And the drive system you mentioned earlier.
Right. By drive system. We have single-wheel drive, which actually applies to all two-wheelers. Only one wheel is driven. Simple, light. Then two-wheel drive, seen in most hatchback cars and sedans, where power goes to just two wheels, usually the front, FWD, or the rear, RWD. Offers a good balance of efficiency and traction for normal roads. And finally, four-wheel drive, 4WD or AWD, common in racing cars, Jeeps, SUVs, and heavy-duty trucks. Here, all four wheels receive power, which massively enhances traction, control, especially in off-road conditions, snow, or for performance driving.
And lastly, how the gears change.
Correct. By transmission system. You have conventional, which means a manual gearbox with a clutch pedal. Then semi-automatic, which might automate the clutch but still require gear selection. And fully automatic transmission systems, which handle all gear changes themselves. Each offers different levels of driver control, convenience, fuel economy, and performance characteristics.
So, when you look at this incredible diversity and specialization in vehicle design, what does it all really mean for us as drivers or passengers? It's not just about having a car. It's about having a highly optimized machine for a very specific role, isn't it?
Exactly that. It means that every single vehicle you encounter on the road, from that tiny scooter zipping through traffic to a massive 18-wheeler hauling tons of goods, is the end result of engineers making highly specific, calculated design choices.
Choices based on?
based on its intended function, the environment it's likely to operate in, the desired performance characteristics, speed, economy, load capacity, and even regulatory requirements like safety and emission standards. This deep understanding of classification isn't just academic. It allows for targeted innovation and continuous improvement across the entire automotive spectrum. Ultimately, it gives us the right tool for almost every conceivable mobility need.
Okay, after dissecting the powerful heart of the car, the engine, and seeing how its raw energy gets converted and transmitted, let's turn our attention to the underlying framework, the structure that holds this entire marvel together. What's the very foundation upon which all these complex systems are built? That brings us to the perhaps often unsung hero, the chassis.
That's a great way to put it, the unsung hero. In French, the word chassis literally means something like a frame or structure. In automotive terms, it essentially means a combination of all the systems and components that enable a vehicle to actually run.
So basically the car without the pretty bits.
In essence, yes. It's a vehicle without its outer bodywork, the shell you see. It includes almost all the major functional units of a vehicle. You've got the basic structural framework itself, which provides the foundational rigidity and support, the skeleton, if you will. Then the prime mover, which is the engine. All the auxiliaries, things like the fuel tank, the cooling system, radiator hoses, and the electrical components, battery, alternator. The controls, naturally the steering mechanism and the braking system components, and the entire transmission system we just discussed, which delivers power to the wheels. All these essential parts are mounted onto this core structure, making it the central backbone of the vehicle.
So it's truly the core structural and mechanical backbone. And how are these components typically put together in terms of the chassis' fundamental construction?
Right.
Are there different philosophies or main approaches engineers take?
Yes, there are two main construction methods that really define how these components are integrated, how the whole thing is built. The first is what we call conventional construction. This uses a separate, distinct frame.
Like a ladder.
Exactly like a ladder frame in many cases, especially for trucks and older vehicles. In this method, the main structural frame is built independently, often as this strong ladder-like structure made of steel rails. Then the engine, the transmission, the suspension components, and finally the body are all bolted or mounted onto this separate frame.
What's the advantage of that?
Well, this approach offers great robustness and flexibility, especially for heavy-duty applications like trucks or serious off-roaders. It can handle high loads and stress as well, and it allows for relatively easy body swaps or modifications because the body isn't the primary structure.
Okay, and the second method?
The second method, and the one you'll find in the vast majority of modern passenger cars today, is unitary or frameless construction. It's often called a monocoque body or unibody.
Unibody, yeah, I've heard that.
Right. In this design, there's no separate heavy frame. Instead, the vehicle's outer body itself, the floor pan, the side panels, the roof structure, is meticulously designed and engineered to provide the entire structural integrity and rigidity for the vehicle. It acts as the primary load-bearing component, and all the mechanical parts, like the engine and suspension, are directly attached to reinforced points on this body structure.
And why is that so common now?
It's brilliant because it's typically much lighter than a separate frame design, which helps with fuel economy and performance. It generally offers better crash protection because impact forces can be distributed more effectively through the entire structure. And it usually allows for lower manufacturing costs and better space utilization inside the car as you don't have a bulky frame intruding.
Okay, that makes sense. Now, beyond the basic construction method, how do engineers think about the chassis based on something really fundamental like where the engine actually sits or how power is ultimately delivered to the wheels? Does that change the chassis classification?
Oh, absolutely. The position of the engine within the chassis significantly impacts several critical aspects of a vehicle. Things like space utilization inside, the vehicle's weight distribution front to rear, which is crucial for handling, and ultimately, its overall driving dynamics and stability characteristics.
So what are the main layouts?
Let's look at the classifications based on engine position first. You can have the engine at center chassis. Here, the engine is mounted centrally within the vehicle's wheelbase, typically between the front and rear axles, often just behind the passenger compartment.
Like in sports cars.
Exactly. This arrangement allows for optimal weight distribution, close to 50-50 front-rear, contributing to superior handling, balance, and agility. That's why you see it in high-performance sports cars or specialized race cars. It can also allow for full utilization of the chassis floor space in certain designs, though maybe not for passengers.
Okay, what's next?
Then there's the conventional chassis. This is probably the most common layout historically. The engine is fitted at the front of the vehicle, typically ahead of the driver's seat or cabin, under the hood or bonnet.
Most cars, basically.
Yes, very common and practical for many passenger cars and trucks. It offers good accessibility for maintenance, but it does mean that the engine occupies a portion of the vehicle's potential interior or cargo space at the front.
Right.
Then you have the full forward chassis. This takes the engine placement a step further, with the engine fitted completely inside the driver's cabin, often between or slightly behind the front seats.
You see that in vans sometime.
Precisely. This layout is often chosen in light commercial vehicles or vans to absolutely maximize the rear cargo space. The trade-off can be increased cabin noise and heat, and maybe reduced legroom.
Makes sense.
A variation is the semi-forward chassis. Here, the engine is positioned so that roughly half of it is in front of the driver's cabin structure, and the other half actually protrudes into the cabin area, often under a cover or doghouse. This is a compromise sometimes seen in larger trucks and some older buses, balancing load space needs with engine accessibility.
Okay. And the last one.
Finally, we have the engine at rear chassis. As the name implies, the engine is fitted at the very rear of the vehicle, usually behind the rear axle. This type of chassis is mostly found in larger buses, which is why it's also commonly referred to simply as a bus chassis.
Why put it there?
It frees up the entire front and middle sections of the vehicle for passenger seating or luggage, making it highly efficient for public transport design. It also keeps engine noise and heat away from the passengers.
Clever. Now, you also mentioned classifying by drive wheels.
Yes, chassis can also be classified by the number of wheels that are actually driven by the engine. This is often denoted by that useful X notation, which gives a quick insight into the vehicle's traction capabilities.
Right, like 4x2 or 4x4.
Exactly. A 4x2 drive chassis means there are 4 wheels total on the vehicle, but only 2 of those wheels are the driving wheels. These could be the rear wheels, rear-wheel drive, RWD, or the front wheels, front-wheel drive, FWD. This offers good efficiency for regular road use.
A 4x4.
A 4x4 drive chassis also has 4 wheels in total, but in this case, all 4 are driving wheels. This is crucial for getting superior traction in challenging conditions. Think off-road terrain, snow, mud, or for performance cars needing maximum grip during acceleration.
And bigger vehicles.
Moving to larger vehicles, you might see a 6x2 drive chassis. This means the vehicle has 6 wheels in total, usually 3 axles, but only 2 of those wheels, typically on one of the rear axles, provide the drive. This is common in some configurations of trucks or buses.
Okay.
And a 6x4 drive chassis means 6 wheels total, but with 4 of those wheels providing the drive, usually across 2 rear axles. This is often seen in heavy-duty trucks, dump trucks, and articulated vehicles where much greater traction and immense load carrying capacity are required to move massive weights, especially on construction sites or over difficult terrain.
That X notation is so clear once you know what it means. It really does speak volumes about the vehicle's capability and its intended design purpose. It tells you at a glance what kind of job it's built for.
Precisely. It's a succinct and universal way for engineers, fleet managers, and even knowledgeable buyers to communicate the fundamental drive characteristics. And those characteristics directly influence a vehicle's performance, its stability, its fuel consumption, and its suitability for various tasks, from agile city driving all the way up to hauling heavy loads over really difficult ground. It's a key piece of information.
Let's talk about the front end now, particularly those foundational components that dictate where you go when you turn the wheel. The front axle beam sounds pretty crucial. What's it actually made of, and what specific jobs does it do to keep the front of the vehicle stable and steerable?
It's an incredibly robust component, specifically engineered to handle immense forces day in, day out. It's typically forged as a single piece of steel, a process called drop forging, often using steel with around 0.4% carbon, or for extra durability, maybe a 1-3% nickel steel alloy.
Why those materials?
The exact material choice is critical because this beam has to withstand significant bending loads from the vehicle's weight, plus impact loads from bumps and twisting forces during braking and cornering, all without permanently deforming. Reliability is paramount.
And its shape. You mentioned an I section.
Yes, the axle beam itself usually features an I section in its central region. That I shape isn't arbitrary at all. It's a brilliant piece of structural engineering. It provides maximum strength and stiffness to resist bending forces, but using minimal material, which is crucial for keeping weight down. Less weight, especially unsprung weight, means better handling and efficiency.
So, what are its main functions?
Its main functions are absolutely critical. First, it carries the static weight of the entire front part of the vehicle engine, bodywork, everything. Second, it provides the mounting points and structural support to facilitate steering operations, allowing the wheels to pivot left and right. And third, it must sustain all those dynamic bending loads from the vehicle's weight bouncing on the suspension and the forces generated during braking.
And it doesn't drive the wheels.
Interestingly, no. Unlike a rear axle in many vehicles, or the front axle in a 4x4, a typical front axle beam in a 2WD car is designed not to transfer power. Its role is purely structural support and enabling steering. It's also supported on spring seats, which are specially made platforms on the beam where the suspension springs sit. This connection helps reduce the unsprung weight of the vehicle, that's the weight not supported by the springs, like the wheels, brakes, and the axle itself. Reducing unsprung weight helps the suspension perform better, allowing the wheels to follow road imperfections more accurately for a smoother ride and better grip.
Okay.
The ends of this axle beam are then connected to the stub axles using components called kingpins, and the front wheels are then fitted onto these stub axles, completing the whole front end assembly.
And it's connected to something called stub axles by kingpins. Now, for our listener who might not be familiar, what exactly are those parts and why do we need them to make our vehicles steer properly and support the front end weight?
Right. The stub axle is essentially an intermediate small shaft. It's positioned directly between the wheel hub and the end of the main front axle beam. Think of it as the pivot point the wheel attaches to.
Okay, a pivot shaft.
Exactly. And because it handles a lot of stress, it's engineered from very tough materials like 3% nickel steel or various other alloy steels containing elements like molybdenum and chromium. These ensure extreme durability under the constant stress of rotation, load-bearing, and steering forces.
How does it connect?
One end of the stub axle connects to the end of the front axle beam, usually via the kingpin, acting as that crucial pivot point for steering. The other end of the stub axle is what the front wheel hub actually mounts onto and rotates around. You'll often find components like phosphor bronze bushes, or nowadays more likely needle roller bearings, fitted within the connecting parts, providing low-friction bearing surfaces for smooth rotation and steering movement as the wheel turns left or right.
And are there different types?
Yes, there are 4 primary types of stub axles that have been developed over the years, each with a slightly different configuration reflecting engineering refinements and solutions to specific geometry challenges. First, there's the Lemoyne stub axle. In this design, the spindle, the part the wheel mounts on, and the steering knuckle, the part that connects to the steering linkage, are arranged in a sort of L shape.
Okay.
Then you have the inverted Lemoyne stub axle. Similar concept to the Lemoyne, but with a key difference in geometry. The wheel axis is positioned below the main axle beam centerline rather than above it. This alters the steering geometry slightly.
Right.
Next, we have the Elliott stub axle. In this design, the kingpin, that vertical pivot pin, is permanently fixed in the stub axle forging itself. Its ends then turn within a forked end on the main axle beam.
And the last one, the common one.
The last one, and the type most commonly used in automobiles today, is the reversed Elliott stub axle. Now, this isn't just a minor variation. It's a really brilliant piece of practical engineering for maintainability. In this design, the kingpin is fixed directly in the end of the axle beam. Its ends then turn within the forks of the steering knuckle, which is part of the stub axle assembly.
Why is that better?
This seemingly small change is highly advantageous. It means if those critical bearing surfaces within the knuckle wear out, which is a common issue over many miles, they can be repaired or replaced relatively easily, often by replacing bushes or bearings within the knuckle itself without causing damage to the main expensive front axle beam. This dramatically simplifies maintenance, reduces repair costs, and significantly extends the functional life of the entire front axle component, impacting the vehicle's long-term cost of ownership.
So these little components, the stub axles and kingpins, are actually critical for the very basic ability to steer the car and support its weight accurately. They're doing a lot of heavy lifting and precision work behind the scenes, aren't they? It's really remarkable how much thought goes into parts we rarely even see or think about.
They absolutely are. Without them, the complex movements required for steering wouldn't be possible, or at the very least, would lead to incredibly rapid component failure and an unstable, unsafe ride. Their precise design and the evolution, like the reversed Elliott type, reflects centuries of engineering refinement aimed squarely at reliability, safety, and practical maintainability over the life of the vehicle.
Okay, we've talked about the hardware, the axles, and the kingpins that allow the wheels to turn. But effective steering isn't just about turning the wheel. There's a whole science to wheel alignment. What exactly is it, and why is it so vital for a vehicle's performance, its safety, and even how long your tires last?
You're right. Wheel alignment is much more than just making sure the steering wheel looks straight. It refers to the precise setting and adjustment of the front wheels and the entire steering mechanism relative to each other and to the vehicle's chassis. This precision is achieved to facilitate several really critical outcomes for the vehicle's operation.
Like what specifically?
Well, first, it ensures easy and predictable directional control. It allows the driver to effortlessly guide the vehicle down the road without constantly needing to make small corrections to the steering wheel just to keep it going smoothly.
Yeah.
Second, it promotes parallel rolling of the wheels when the vehicle is moving straight ahead. This is essential for efficiency, minimizing rolling resistance, and preventing unnecessary friction between the tires and the road.
Less drag,
Yeah,
better fuel economy.
exactly. Third, it provides stability to the vehicle, especially while turning. Proper alignment prevents unwanted body roll or erratic behavior during cornering, making the handling feel predictable and safe. And fourth, and this is a big one for owners, it minimizes uneven tire wear. Poor alignment is probably the #1 cause of tires wearing out prematurely or unevenly, which can be a significant and recurring cost.
So it's not just the front wheels.
No, that's a common misconception. Proper wheel alignment also includes the correct alignment of the vehicle frame itself with respect to the front wheels, the precise placement and alignment of the rear axle, because that affects tracking too, and the proper functioning and geometry of the suspension system. All these elements have to work together in concert to ensure optimal vehicle dynamics and tire wear.
And what happens if the wheels aren't perfectly aligned? I've heard terms like toe in and toe out, and it sounds like they can cause some real headaches for drivers, besides just wearing out tires.
Indeed, they can. If the front wheels aren't perfectly parallel while the vehicle is moving straight, they're usually described as either having toe in or toe out. If the wheels are pointing slightly inwards towards each other at the front, meaning the distance between the front edges of the tires is less than the distance between the rear edges, they are said to have toe in.
Okay.
Conversely, if they're pointing slightly outwards, away from each other at the front, meaning the distance between the front edges is more than at the rear, they have toe out.
And both are bad if they're excessive.
Absolutely. Both conditions, if they're beyond the manufacturer's specified tolerances, lead to significant and uneven tire wear. You'll often see one edge of the tire, either the inside or the outside, wearing down much faster than the rest. This drastically shortens tire life. Beyond tire wear, poor alignment also makes steering feel heavier or less responsive, requiring more effort from the driver. It can also cause the vehicle to pull to one side, requiring constant correction. And yes, it can even noticeably increase fuel consumption because the tires are essentially scrubbing sideways against the road rather than rolling smoothly forward.
So if your car feels like it's trying to crab walk down the highway, or if you're replacing tires way too often, poor alignment is probably the prime suspect.
It's definitely one of the first things to check. Proper wheel alignment is absolutely necessary for good steering feel, overall directional stability, maximizing tire life, and getting the best possible fuel economy.
So what influences this alignment? It sounds like a lot of intricate variables need to be precisely balanced for everything to work in perfect harmony.
You're right, it's a complex interplay of many factors. Wheel alignment depends upon several key things. First, there are factors relating directly to the wheels and tires themselves. Things like the overall balance of the wheel and tire assembly and unbalanced wheel can cause vibrations that affect alignment readings and handling.
Okay.
Then there's the correct inflation pressure of the tires. This is often overlooked, but it's crucial. Underinflated or unevenly inflated tires can significantly alter the vehicle's stance and alignment angles. And of course, proper brake adjustment is important too, as uneven braking forces can sometimes pull the alignment out over time.
And the steering parts themselves.
Yes. Then there's the crucial steering geometry. This involves those precise angles we need to talk about. Kingpin inclination, or SAI, camber angle, and caster angle, as well as that intentional or unintentional toe-in or toe-out setting. Finally, the condition of the vehicle's entire network of steering linkages. Tie rods, ball joints, steering rack, and its suspension system components, control arms, bushings, springs, shock absorbers also play a significant role in maintaining correct wheel alignment. Any wear, looseness, or damage in these areas can easily throw the alignment off, highlighting just how integrated all these systems really are.
Let's dive into those angles then, because they sound like the secret sauce to getting precise steering and handling. First up, camber angle. What is it exactly, and why does that subtle tilt of the wheel matter so much?
Okay, camber angle is defined as the tilt of the top of the front wheels either inward or outward from the vertical plane when you're looking at the vehicle from the front.
Inward or outward?
Right. If the top of the wheel tilts outward, away from the vehicle's center line, it's called positive camber. If the top of the wheel tilts inward towards the vehicle's center line, it's considered negative camber.
And what's the goal?
Well, the primary goal in most everyday passenger vehicles is often to achieve close to zero camber angle when the vehicle is moving straight down the road and carrying its normal load. Why? Because zero camber maximizes the contact patch, the area of the tire tread that's actually touching the road.
More contact means more grip.
Exactly. Optimal grip for braking and acceleration, and it also leads to the most even tire wear across the tread, maximizing tire life. However, engineers might intentionally design for a slight positive, or more commonly in performance cars, a slight negative camber.
Why negative for performance cars?
Negative camber helps to improve cornering grip. As the car rolls during a turn, the negative camber helps keep the outside tire more upright relative to the road surface, maintaining a better contact patch when it's needed most. But for most cars, the camber angle shouldn't exceed about 2 degrees in either direction for practical driving and tire wear purposes.
Okay, so camber affects tire wear and cornering grip. What about caster angle? How does that influence the drive, and why is it so important for stability, for making the car want to go straight?
Caster angle is the angle between the steering axis, which you can visualize as an imaginary line drawn through the upper and lower pivot points, like the kingpin or ball joints, and the true vertical line when viewed from the side of the vehicle.
Like the angle of a bicycle fork.
That's another excellent analogy. Or think about the wheels on a shopping cart, how they trail behind the pivot point. If the steering axis, that imaginary line, is tilted backwards at the top, meaning the bottom pivot point is ahead of the top pivot point relative to the direction of travel, it's referred to as positive caster.
And if it tilts forward?
If it's tilted forward at the top, meaning the bottom pivot is behind the top one, that's negative caster, though negative caster is very rare in modern cars.
Okay. And what's the practical impact of having positive caster? Why is it generally seen as beneficial?
Positive caster is highly beneficial and is intentionally designed into almost all vehicles precisely because it provides crucial directional stability. It creates a self-centering effect on the steering.
Why does it do that?
Just like those shopping cart wheels naturally align themselves to follow the direction you're pushing the cart, positive caster makes the vehicle's front wheels want to naturally return to a straight-ahead position after you make a turn. This minimizes the tendency for the vehicle to wander or drift off course, reducing the driver's effort needed to keep it pointed straight, especially at higher speeds.
So it makes driving less tiring.
Yes, and safer. Crucially, it also helps to prevent oscillations or shimmy, that unnerving wobble of the front wheels that can sometimes occur at certain speeds if the caster isn't right. An ideal caster angle for most cars is usually kept somewhere around 3 degrees positive, maybe a bit more, finding a good balance between stability and steering effort. Because too much positive caster can make the steering feel heavy.
And negative caster.
Negative caster, conversely, provides very poor directional control and stability. It would make the vehicle feel unstable, twitchy, and very difficult to keep tracking straight.
And the last of the main angles, kingpin inclination or KPI. Is that related to the kingpin we discussed earlier, that crucial pivot point for steering?
Yes, it is directly related, and it works together with camber to define the steering geometry. Kingpin inclination, also sometimes known more technically as steering axis inclination or SAI, is the angle that the steering axis, that same imaginary line through the pivot points, is tilted inward towards the center of the vehicle when viewed from the front.
So it's an inward tilt of the pivot line.
Exactly. While in many modern cars, separate upper and lower ball joints have largely replaced the traditional single kingpin, the underlying principle of this geometric angle remains absolutely vital for steering geometry and feel.
Why is it important? What does it do?
Kingpin inclination, or SAI, is important for a couple of reasons. Firstly, it helps to keep the front wheels pointing forward in a stable manner by reducing the scrub radius, that's the distance between where the steering axis hits the ground and the center of the tire contact patch. Reducing this minimizes steering kickback from bumps. More importantly, perhaps, it works with caster to generate a self-centering effect. As you turn the steering wheel away from straight ahead, the SAI causes the vehicle body on that side to lift slightly. It's like you're trying to lift the car's weight as you turn. This weight then naturally wants to push the wheel back down and return it to the straight-ahead position when you release the steering wheel. This reduces the effort the driver needs to apply for steering returnability.
How much tilt are we talking about?
This angle is usually carefully designed by the engineers and kept within a range of roughly 3 to 9 degrees, sometimes more depending on the vehicle design, to achieve the optimal balance of steering feel, stability, and returnability.
You mentioned toe in and toe out earlier,
Yeah.
primarily as a consequence of poor alignment. But you also hinted it's sometimes a designed aspect, right? A subtle tilt that's actually intentionally put there for a reason.
That's an excellent and important distinction to make. While excessive toe in or toe out is indeed detrimental, a symptom of misalignment that causes problems, a slight amount of toe in is actually intentionally designed into almost all modern vehicles. Heavy-duty tractors might be an exception due to their specific low-speed, high-load operational requirements. They sometimes use toe out.
Okay, so for cars, usually a little toe in.
Yes. When we talk about intentional toe-in, it means that the distance between the very front edges of the two front tires is designed to be slightly less than the distance between the rear edges of those same tires when the wheels are pointing straight ahead. They're angled slightly towards each other.
So why is this intentional slight inward tilt needed? What purpose does it serve for driving stability and maybe even tire longevity if it's set correctly?
It's provided specifically to offset the various forces acting on the wheels that naturally tend to make them splay outwards or toe out when the vehicle is actually moving forward under power.
What kind of forces?
These forces include things like the rolling resistance of the tires, slight deflections in the suspension bushings under load, and even the effect of road crown, that slight curvature built into most roads for drainage, which tends to push the vehicle slightly downhill.
Ah. Okay.
So this slight initial toe-in actively counteracts that tendency of the wheels to toe out dynamically. The idea is that when the vehicle is rolling down the road at normal speeds, the forces pushing the wheels outward effectively cancel out the initial toe-in setting, resulting in the wheels running almost perfectly parallel.
So the goal is parallel rolling while driving.
Exactly. This ensures the wheels track straight and true down the road, contributing to better directional stability, reducing that scrubbing effect we talked about, and ultimately minimizing uneven tire wear when it's properly set by the manufacturer. It's a crucial fine-tuning adjustment that significantly impacts the overall handling, feel, stability, and the lifespan of your tires, making your drive smoother, safer, and more efficient in the long run.
Okay, we've seen how the engine starts and converts its explosive motion into rotation, and how those subtle alignment angles are absolutely crucial for steering precisely. Now, once that power is generated by the engine, how does it actually get to the wheels in a controlled, adaptable manner? We need to be able to change speeds, handle hills, cruise efficiently. That's the intricate job of the transmission system, isn't it?
Precisely. The transmission system, in its broadest sense, refers to the entire drivetrain, everything that carries power from the engine to the driving wheels. This complex assembly typically includes the clutch in manual vehicles, the gearbox or transaxle, the propeller shaft, especially vital for rear-wheel drive vehicles, universal joints, the differential gear assembly, and finally the drive axles connecting to the wheels.
And its main job.
Its core purpose is to transmit the mechanical power, specifically the engine's torque and rotational speed, from the crankshaft to the driving wheels of the automobile. But crucially, it doesn't just transmit it, it manages it, allowing the driver or the system to adapt the power delivery to suit different driving conditions efficiently.
Okay, let's unpack this mechanism step by step then. Can you walk us through the journey of power from the engine to the wheels, explaining how each of those components you mentioned contributes to that controlled motion?
Certainly. So when the engine is running, we have the pistons reciprocating up and down motion within the cylinder. As we discussed, this gets converted into the rotary or spinning motion of the crankshaft via the connecting rod.
Right, the spinning crankshaft.
This rotation of the crankshaft is the raw power output of the engine. This rotation is then transmitted first to the gearbox. But this connection happens via the clutch.
The gatekeeper.
The gatekeeper, exactly. The clutch allows us to temporarily disengage the engine's power from the rest of the drivetrain necessary for starting from a stop, stopping without stalling, or changing gears in a manual transmission, and then to smoothly re-engage it.
Okay, then the gearbox.
Right. The power flows into the gearbox. The gearbox, with its internal set of gears of different sizes, is where the vehicle's speed and torque are meticulously regulated. It essentially trades speed for torque, or vice versa. Low gears provide high torque for acceleration or climbing hills, while high gears provide higher speed for cruising efficiently. The driver selects the appropriate gear ratio,
Or the automatic transmission does.
or the automatic transmission selects it. From the gearbox, the regulated rotational motion is transmitted typically to the propeller shaft in RWD or 4WD.
A bridge to the back.
The bridge to the back, yes. This shaft spins and carries the power towards the driving axle. Along the way, it usually has universal joints. These are critical flexible couplings that allow the shaft to transmit power even when the angle between the gearbox and the rear axle changes due to suspension movement.
We talked about those. Very important.
Very important. The propeller shaft then connects to the differential gear assembly, housed within the drive axle. The differential performs two key jobs. It turns the direction of rotation by 90 degrees to drive the axles, and, as we mentioned, it allows the wheels on either side to rotate at different speeds during turns.
Right.
Finally, the power is transmitted from the differential out through the drive axles, or half shafts, to the driving wheels, causing them to roll and the vehicle to move. It's quite a journey.
It really is. And what about four-wheel drive vehicles, or say two-wheelers like motorcycles? Do they have the exact same setup, or are there significant variations to this elaborate power chain?
No, not entirely the same, and this really highlights the adaptability of engineering solutions to different needs. In a four-wheel drive vehicle, you typically have an additional component called a transfer box or transfer case.
What does that do?
Its role is quite clever. It usually sits behind the main gearbox, and its job is to split the power and distribute it between both the front and rear axles. Often, it allows the driver to select between 2WD and 4WD modes, and sometimes includes an additional low-range gear set for serious off-roading, multiplying torque even further. It ensures power goes effectively to all four wheels when needed for maximum traction.
And two-wheelers, much simpler.
Much simpler generally. Two-wheelers, like motorcycles or scooters, have a much more compact power transmission system, optimized for their lighter weight and agility. They don't usually have a separate propeller shaft running the length of the vehicle or a complex differential gear assembly. Instead, they typically use a direct chain drive, or sometimes a belt drive, or even a shaft drive in some larger bikes, to transmit power straight from the gearbox output shaft directly to the rear wheel sprocket. This simplicity translates to fewer components, less weight, and often less power loss in the drivetrain.
So despite these variations for different vehicle types, what would you say are the absolute core components that are always part of a comprehensive transmission system, the fundamental building blocks?
Well, if we consider the whole system from engine to wheel, the essential components that form the functional backbone of nearly all powertrain transmission systems, though their specific form or complexity might vary quite a bit, are typically the clutch, or torque converter in automatics, the gearbox, or transaxle combining gearbox and differential, universal joints, or CV joints in FWD, the propeller shaft, if applicable, the differential gear assembly, except in most two-wheelers, and the final drive axle. Each one plays a distinct and crucial role in ensuring the smooth, controlled, adaptable, and efficient transfer of power.
Okay, now let's switch gears, so to speak, to the other crucial half of vehicle control: steering. We know the driver turns the wheel, but if that steering wheel was directly connected mechanically to the front wheels, it would be incredibly difficult, maybe impossible to turn them, right? Especially at low speeds or when stationary because of the sheer weight resting on those front tires.
Absolutely. The forces involved would be enormous.
That's where the steering gear comes in. It acts as a brilliant effort reduction system, multiplying our input.
Yes, precisely. The steering gear is the mechanism that amplifies the driver's relatively small steering effort, making it manageable to turn the wheels. It's designed with a specific gear reduction ratio, often called the steering ratio. This moment ratio typically ranges from about 12 to 1, 12.1 for a very direct, sporty feel, up to maybe 35 to 1, 35.1, or even more for heavy trucks, providing much more assistance.
So a higher number means less effort.
Exactly. A 20.1 ratio means that for every 20 degrees you turn the steering wheel, the road wheels turn only 1 degree. This multiplies the force you apply. Its main functions are therefore twofold. First, as you mentioned, it helps to multiply that small twisting effort, torque, applied by the driver on the steering wheel into a much greater force acting on the steering linkages, like the drag link or tie rods.
And the second function?
Second, and equally important, it functions to transform the purely rotary motion of the steering wheel, that circular movement you make with your hands, into the back and forth, or linear motion that's required by the steering linkages, like a steering rack or a pitman arm connected to a drag link, to actually push and pull the wheels and make them pivot left or right. It's the critical mechanical intermediary between your hands and the road wheels.
What are some common types of steering gears we might find in vehicles today? Or maybe types that have been significant historically in solving this engineering challenge of making steering easy and precise?
Oh, many types exist, and they've certainly evolved over time, aiming for better efficiency, durability, compactness, and driver feel. Some widely used or historically significant ones include, first, the worm and wheel steering gear. This was quite common in older cars and trucks. Here, a worm, which is essentially a spiral gear fixed on the end of the steering column shaft, meshes with a worm wheel, which looks like a regular circular gear.
Oh, the work.
As the steering wheel turns the worm gear, the worm spiral thread forces the worm wheel to rotate, but only through a limited arc, typically maybe 60 to 80 degrees for full lock-to-lock steering. This rotational motion of the worm wheel then causes a drop arm or pitman arm, which is attached to the wheel's spindle, to swing back and forth. This arm is then connected to the rest of the steering linkages, like a drag link, to move the wheels. The whole gear mechanism is enclosed in a sturdy casing, usually made of robust cast iron or sometimes aluminum alloy, and it's filled with heavy gear oil for continuous lubrication, which is essential to reduce friction and wear between the worm and wheel.
Okay, that sounds quite mechanical. What else?
Then there's a variation called the worm and worm sector steering gear. This was developed as a more cost-effective and compact version of the full worm and wheel. The key insight here was realizing that in the full worm and wheel system, only about a quarter or less of the worm wheel's teeth are actually engaged and utilized during the entire steering range. So this variation cleverly uses only that necessary fractional part or sector of the worm wheel. This makes the whole assembly smaller, lighter, and cheaper to manufacture and install without really sacrificing functionality for typical steering angle requirements.
Smart optimization.
Very much so. Another type is the worm and nut steering gear, sometimes called worm and roller. This design features a long steel nut with internal threads that precisely engages with the worm on the steering shaft. A small peg or a roller is often provided on the outer surface of the nut, fitting into a groove in the casing, specifically to prevent the nut itself from rotating along with the worm. This forces the nut to only move linearly up and down along the worm shaft as the steering wheel turns. This linear motion is then transferred, usually via levers, to the steering linkages.
Okay. And the recirculating ball type. That sounds interesting.
Ah, yes, the recirculating ball type steering gear. This is a particularly fascinating and quite efficient design, very popular for many decades, especially in larger cars and trucks, often combined with power assistance. It ingeniously incorporates a continuous loop of small, hard steel balls that act like bearings between the worm gear on the steering shaft and a matching nut that rides on it.
Balls reduce friction.
Massively. The nut has coarse-pitched helical grooves on its inside that match the worm's thread, and these steel balls fill the circular channel formed by the grooves of both the nut and the worm. As the steering wheel turns, the nut moves along the worm, but the balls roll between them, allowing for extremely low friction movement and much greater longevity compared to direct metal-on-metal sliding. The balls that exit one end of the nut are cleverly recirculated back to the other end through external tubes or internal passages, hence the name recirculating ball.
And how does it steer?
The outside of this low-friction nut then usually has gear teeth cut into it, which mesh directly with a gear sector attached to the pitman arm. So the linear motion of the nut translates into the swinging motion of the pitman arm, which moves the steering linkages. This design offers a very smooth, durable, and relatively precise steering feel, though maybe not quite as direct as rack and pinion.
Which brings us to...
Exactly. The rack and pinion steering gear. This system is overwhelmingly common today, especially in almost all front-wheel drive cars, smaller rear-wheel drive cars, and SUVs, primarily due to its simplicity, lightweight, directness, and efficiency.
How does that one work?
In the system, a small gear, called a pinion, is mounted on the end of the steering shaft, directly connected to the steering wheel. This pinion gear meshes directly with a long horizontal toothed bar called the rack. The rack usually slides sideways within a housing. As the steering wheel rotates, the pinion gear rotates, and its teeth engage the teeth on the rack, forcing the entire rack to move linearly, either left or right.
And that moves the wheels.
Directly. The ends of the rack are connected, usually via adjustable arms called tie rods with ball joints, to the steering arms or knuckles on the stub axles. So the rack's sideways linear motion is directly translated into the steering angle of the front wheels. This direct connection provides excellent driver feedback and responsiveness, making the car feel agile.
Wow. It's amazing how many different ways engineers have found to solve the same fundamental problem of translating a driver's simple turn of the wheel into precise wheel motion. Each system, like the worm and wheel versus rack and pinion, clearly has its own set of advantages and disadvantages for specific vehicle types and desired performance characteristics.
It absolutely is. Each design represents a very specific set of engineering trade-offs and optimizations. They're balancing factors like the amount of space the mechanism takes up, the manufacturing cost, the amount of physical effort required from the driver or the power assistance needed, the level of road feel or feedback transferred back to the steering wheel, durability, and precision. It really shows how even seemingly simple components in a car are the result of meticulous engineering design, a deep understanding of physics and mechanics, and decades, even centuries, of continuous innovation and refinement.
Okay, shifting gears, it's such a fundamental driving action, whether you're doing it yourself in a manual or the car's doing it for you in an automatic. And the clutch is absolutely central to that whole process, at least traditionally. What exactly is this device? And how does it play such a crucial role in managing the engine's power flow to the rest of the car?
Right. The clutch is a critical mechanical device or mechanism whose primary job is to control the flow of power, specifically the rotational torque from the engine to the transmission system. Think of it as an essential intermediate mechanism, a sort of on-off switch, meticulously placed right between the engine's flywheel, which spins directly with the engine's crankshaft at engine speed, and the input shaft of the gearbox, which needs to be connected or disconnected from the engine's power. It's essentially the gatekeeper of power transfer between those two major components.
So it's fundamentally about connecting and disconnecting that power at the driver's command.
Mm-hmm.
But it's also about doing it smoothly, right, to protect the system from shock.
Exactly. That smoothness is key. In normal driving conditions, when you're cruising along in gear, the clutch remains in an engaged position. This allows power to flow seamlessly and continuously from the engine through the clutch into the gearbox and then ultimately out to the wheels.
Okay.
However, when you need to bring the vehicle to a stable, stopped position without stalling the engine, or, more commonly, when you need to change gears up or down in a manual, the clutch must be disengaged. This action, usually controlled by pressing the clutch pedal, effectively interrupts that power flow. It decouples the engine from the transmission temporarily.
Why is that decoupling so important?
Well, it's not just about allowing gear changes. It also facilitates a gradual take-up of the load when you're starting from a standstill or re-engaging a gear after shifting. This feathering action, controlling the slit between the clutch plates, is absolutely critical. It prevents jerky operations, sudden lurches, and perhaps most importantly, it avoids undue shock loading, those sudden, damaging forces on all the various gears, shafts, and bearings within the transmission system. It protects them from premature wear and potential breakage. Without a clutch, every gear change would be a violent, grinding lurch.
Yeah, I can imagine. What are some of the main types of clutches out there? It sounds like there might be quite a lot of variety for different applications and driving experiences.
There's indeed a wide variety, each designed with specific applications and operational characteristics in mind. Broadly, the most common type in manual cars is the mechanical friction clutch, usually the ubiquitous single-plate clutch. Yeah. This relies on friction between surfaces pressed together.
Like brake pads, almost.
Similar principle, yes, using friction material. Then you have specialized applications. Centrifugal and semi-centrifugal clutches engage automatically based on engine speed, using centrifugal force to press the friction surfaces together. You used to find these in some older automatic transmission systems, and they're still common in things like scooters or chainsaws.
Okay.
There are also less common types these days, like conical spring clutches or very robust dog and spline clutches used for heavy duty, positive engagement where some shock is acceptable, maybe in industrial machinery. And then you get into more advanced systems like hydraulic clutches, vacuum clutches, and electromagnetic clutches. These use fluid pressure, engine vacuum, or electromagnetic force respectively for actuation, often to reduce pedal effort or provide more precise control.
What about multi-plate?
Ah, yes, the multi-plate clutch. This uses multiple, smaller diameter friction plates stacked together. The advantage is that it can transmit much higher torque within a more compact space compared to a single plate clutch of the same torque capacity. That's why you often find them in motorcycles where space is tight, or in some high-performance racing applications, or in heavy equipment transmissions.
Got it. And the basic mechanism, how does pressing or releasing the clutch pedal actually work inside to engage or disengage this vital component? It seems like a simple foot movement, but clearly a lot must be happening mechanically, linkage-wise.
You're right, there's a coordinated sequence of mechanical actions. When the clutch pedal is pressed down by the driver, the linkage system connected to it forces a component called the thrust bearing or release bearing to move inwards towards the engine.
Okay, the bearing moves.
This inward movement of the thrust bearing pushes against a set of release levers, which are part of the clutch cover assembly bolted to the flywheel. As these levers pivot, they pull the main pressure plate, a heavy spring-loaded plate that normally clamps the clutch disc away from the engine's flywheel.
Releasing the pressure.
Exactly. This action also simultaneously compresses the main clutch springs, which could be diaphragm springs or coil springs, within the clutch cover. This combined action effectively removes the clamping pressure from the actual clutch disc, the friction plate splined to the gearbox input shaft, allowing it to move back slightly away from the flywheel. This breaks the friction connection, thereby interrupting the power flow from the engine to the gearbox.
And releasing the pedal.
Releasing the pedal does the exact opposite. The thrust bearing moves back away from the levers, usually pulled by a return spring. This allows the main clutch springs, like the diaphragm spring, to expand again, pushing the pressure plate powerfully back towards the flywheel. This clamps the clutch disc firmly between the pressure plate and the flywheel surface, re-establishing the friction connection and smoothly re-engaging the power flow.
The clutch plate itself, the disc in the middle, that has some interesting features too, doesn't it? It's not just a flat piece of metal with friction material, but it's designed for both robust power transfer and that smooth engagement you mentioned.
Yes, absolutely. A conventional clutch plate, or friction disc, used widely in automobiles, is far more complex and cleverly engineered than it might appear at first glance. It primarily consists of a central circular steel plate with a splined hub in its center. These splines allow it to slide axially along the correspondingly splined input shaft of the transmission while still transmitting torque. Critically, for achieving that smooth engagement and absorbing some of the initial shock, what's called axial cushioning is often provided. This is usually located between the main steel plate of the disc and the friction facings riveted or bonded to its sides.
How is that cushioning achieved?
It's often achieved using specially shaped, curved, or wavy spring segments, sometimes called Marcel springs or cushioning springs, sandwiched between the plate and the facings. Many of these spring segments might be attached at equal intervals around the periphery. This inherent waviness or springiness of the segments significantly enhances the cushioning effect as the clutch engages, compressing slightly to provide that essential smoothness and prevent grabbing.
And what about vibrations?
Good question. To absorb unacceptable torsional vibrations that can arise from the engine's firing impulses, the slight unevenness in power delivery, as each cylinder fires the clutch plate is often made in two main concentric parts. There's a central hub subassembly, splined to the gearbox, and an outer-facing ring assembly, carrying the friction material. These two parts are then connected to each other through a series of small coil springs, called damper springs, arranged circumferentially within windows in the plate. These springs allow a small amount of relative rotational movement between the hub and the outer ring, effectively damping out those torsional vibrations before they reach the gearbox, making the drivetrain feel smoother and quieter. And finally, you'll often notice that the clutch plates themselves, or at least the friction facings, are usually perforated or have grooves cut into them. This isn't just for show, it's to allow for efficient dissipation of the significant amount of heat that's inevitably produced in the clutch due to the friction generated during engagement, and especially during periods of slip. Without these perforations or grooves to help air circulate and carry heat away, the clutch could quickly overheat, leading to fade, loss of friction, or even complete failure.
Right. Now, while these mechanical friction clutches are incredibly common, there's another fascinating way to transmit power, especially in automatic transmissions or industrial applications. Fluid coupling, sometimes called a hydraulic coupling. What is this, and how does it manage to work, given that there's apparently no direct mechanical contact between the input and output? It sounds almost counterintuitive for transferring significant power.
It is an elegant solution, particularly valued where exceptionally smooth, shock-free power transfer is the top priority. A fluid coupling is essentially a hydrodynamic device. It transmits rotating mechanical power from an input shaft to an output shaft purely through the movement of a liquid medium, which is usually a specialized oil, rather than through direct, solid metal-on-metal contact like a friction clutch.
So it's all done with oil. How is it built?
It consists of two main rotating components housed within a sealed casing. First, you have a pump, often called the impeller, which is attached directly to the driving shaft, connected to the engine's crankshaft. Second, you have a turbine, sometimes called the runner, which is attached to the driven shaft, connected to the transmission's input. The key here is that there's no direct physical mechanical contact between this pump impeller and the turbine runner. They face each other with a small gap between them, and they are both completely enclosed in that single outer casing or shell, which contains the hydraulic fluid, the oil. The oil in this casing is the sole medium that transmits the momentum, and therefore the torque, from the pump impeller spinning with the engine over to the turbine runner connected to the transmission.
Okay, so the oil is the medium. How does that actually translate into power, getting from the driving shaft to the driven shaft without any direct gears or plates touching? It seems like there'd be a lot of slip.
There is slip, especially at lower speeds, and that's actually part of how it works smoothly. When the driving shaft, connected to the pump or impeller, begins to rotate due to the engine running, the impeller acts like a centrifugal pump. Its vanes catch the oil and fling it outwards towards its outer periphery due to centrifugal force. As it does this, the oil gains speed and kinetic energy.
Okay, oil gets thrown outwards.
This high-velocity oil is then directed across the small gap and flows into the vanes of the turbine runner, which faces the impeller. As the oil flows through the precisely shaped vanes of the turbine, it imparts its energy, its momentum, onto the turbine, causing it to want to rotate. The oil then flows back inward towards the center of the turbine and returns to the eye or center of the pump impeller to repeat the cycle, creating a continuous toroidal or donut-shaped flow pattern within the casing.
So the faster the engine spins.
The faster the engine spins the pump impeller, the more energy is imparted to the oil, and the greater the torque exerted by this flowing oil on the turbine runner becomes. This torque continuously increases as the engine speed rises. Eventually, the torque exerted by the oil becomes sufficient to overcome the inertia or resistance of the driven unit, the transmission, and the rest of the vehicle. At this point, the power is effectively transmitted across the fluid gap, and the driven shaft connected to the turbine begins to rotate, smoothly transferring the engine's power without any harsh mechanical jolt.
What's truly fascinating here, as you said, is that it allows for a very different driving experience compared to a traditional mechanical clutch. Almost seamless, especially when starting off.
Yes, you're right. Fluid coupling provides exceptionally smooth power transmission. It inherently eliminates the jerks and potential roughness that can sometimes be associated with the engagement, especially the abrupt engagement of mechanical clutches. This leads to a notably smoother takeoff from a standstill. The car just glides away, and it significantly reduces wear and strain on all the components within the drivetrain because there are no harsh engagement shocks.
Is it efficient?
Its efficiency is actually quite high at higher engine speeds when the speed difference, the slip between the pump impeller and the turbine runner, is small, maybe only 2-3%. However, its efficiency naturally lowers significantly at lower engine speeds or when there's a large speed difference between input and output, because more energy is lost as heat due to the shearing of the fluid. This inherent slip is what provides the smoothness, but it comes at the cost of some efficiency, particularly at lower speeds or during acceleration. This is why modern automatic transmissions often use a more complex device called a torque converter, which is based on the fluid coupling but adds a third element, a stator, to multiply torque at low speeds, and often includes a lockup clutch to eliminate slip altogether at cruising speeds for better fuel economy.
Oh, okay. And where do we see these pure fluid couplings being used today, beyond just being the ancestor of the torque converter? Are they still used in other applications?
Oh, yes. Pure fluid couplings are still widely used in various industrial applications, often with both electrical motors and internal combustion engines as the prime movers. Their key advantage remains that smooth, shock-free power transmission. They are particularly valuable in applications where gradual starting is critical or where large initial inertial loads need to be overcome without stalling the motor or damaging the machinery.
Like what sort of things?
Think about starting up huge industrial fans or pumps, or long conveyor belt systems in mining or manufacturing. Trying to instantly connect a powerful motor to such a massive inertia with a direct mechanical clutch could cause huge electrical surges or break mechanical parts due to the shock loading. Fluid couplings allow the motor to start up under light load and then smoothly and gradually accelerate the heavy machinery up to speed, protecting both the motor and the driven equipment. They're also used in some railway applications, like in diesel hydraulic locomotives, for power transmission, again, providing that very smooth startup. And yes, they were used as an alternative to mechanical clutches in some early automatic or semi-automatic transmissions. It's truly an elegant and durable solution for achieving smooth, gentle power application across a surprisingly diverse range of heavy-duty machinery.
Okay, we successfully traced the journey of power from the engine through the controlling mechanisms of the clutch and gearbox. But in many common vehicle layouts, like rear-wheel drive cars or trucks, how does that rotational power actually get from the gearbox, which is often near the front, all the way back to the rear axle where the driving wheels are? That sounds like the specific job of the propeller shaft, right? Also sometimes called a drive shaft, or even a cardan shaft.
It is indeed the mechanical bridge that spans that gap. The propeller shaft, or drive shaft, is the component whose primary function is to transmit the rotational drive, the torque, from the output of the transmission system or gearbox, typically located towards the front or middle of a vehicle, back to the input of the differential assembly housed in the rear drive axle.
What's it typically made of?
It's usually constructed from a high-strength steel tube, making it hollow to save weight while maintaining torsional rigidity. Sometimes, for very high torque applications, it might be a solid circular bar. And critically, regardless of whether it's hollow or solid, it must be meticulously dynamically balanced.
Why is balancing so important?
Because this shaft spins at very high speeds directly related to the vehicle's road speed and top gear. Any slight imbalance would cause it to wobble or whip as it rotates. This would lead to undesirable vibrations felt throughout the vehicle, increased noise levels, and could put significant stress on the universal joints, bearings, and transmission seals, potentially causing premature failure or damage. So, balancing is absolutely crucial for smooth, quiet, and reliable operation.
What are its main components? It sounds like there must be more to it than just a simple, rigid spinning tube, given all the movement that happens with the suspension.
You're perceptive to notice that inherent challenge. A propeller shaft assembly primarily consists of 3 essential parts specifically designed to manage those movements and angle changes. There's the main shaft tube itself, then crucial flexible joints called universal joints, often U-joints, and finally, often incorporated, is a sliding joint or slip yoke.
Okay, let's break those down. The shaft.
The shaft is the main tubular component we just discussed. Its job is simply to connect the output shaft of the transmission to the input pinion shaft of the differential, spanning the distance between them. Now, the challenge arises because while the engine and transmission are usually rigidly or semi-rigidly attached to the vehicle's frame or unibody structure,
Right.
the rear axle assembly, containing the differential and the wheels, is attached to that same frame or body via springs, the suspension system. This means the rear axle is constantly moving up and down relative to the frame as the vehicle goes over bumps or dips in the road. This inherent movement means the angle and the distance between the gearbox output and the differential input are constantly changing.
So that's where the joints come in.
Exactly.
Yeah.
This leads us directly to the next crucial component, the universal joints.
The universal joints, or U-joints, they sound really important for dealing with those constantly changing angles and movements between the transmission and the rear axle. How do they actually allow for power transfer when the shafts aren't perfectly aligned in a straight line?
They are absolutely essential for this exact reason. A universal joint is a specific type of flexible coupling designed to connect 2 shafts whose rotational axes might intersect at an inclined and often varying angle. It allows power, the rotational torque, to be transmitted smoothly between these shafts even when there's a significant angular misalignment between them, or when that angle is constantly changing due to suspension movement.
How many are usually used?
A typical propeller shaft in a rear-wheel drive car might incorporate one universal joint at the front end, connecting to the gearbox, and another one at the rear end, connecting to the differential pinion flange. If 2 U-joints are used, which is common, there's often a sliding joint incorporated somewhere along the shaft's length, usually at the front U-joint connection, a slip yoke.
And why are they so indispensable?
When the vehicle encounters irregular road surfaces, the suspension springs compress and expand. This causes the entire rear axle assembly, including the differential, to move up and down relative to the vehicle's frame or body. As it moves, the angle of the propeller shaft relative to both the gearbox output and the differential input changes continuously. Universal joints are essential because they accommodate these dynamic changes in drive angle smoothly. Without them, the drive shaft would bind up, causing severe vibrations, immense stress on the bearings and shafts, and would likely lead to rapid failure or damage to the entire drivetrain. They ensure a smooth, uninterrupted flow of power regardless of the road conditions or suspension articulation.
And the sliding joint you mentioned. What's its specific role, especially given that the propeller shaft might also need to adapt to changes in length as the suspension moves up and down?
That's exactly its purpose. A sliding joint, often integrated into the front U-joint assembly as a slip yoke, is ingeniously designed with internal and external splines. These are interlocking longitudinal grooves and ridges cut into the transmission output shaft and the inside of the yoke part of the propeller shaft.
Splines allow sliding.
Yes, these splines allow the propeller shaft yoke to slide slightly fore and aft along the transmission output shaft, while still remaining rotationally locked to it by the interlocking ridges. This sliding capability is crucial because it permits variations in the propeller shaft's effective operational length.
Why does the length need to change?
As the vehicle's suspension compresses or extends when it goes over bumps, dips, or even just due to load changes, the distance between the fixed gearbox and the moving rear axle actually changes slightly. Its basic geometry as the axle moves up and down in an arc defined by the suspension length, the direct distance to the gearbox changes. Without a sliding joint to accommodate these small but significant variations in length, the propeller shaft would be subjected to immense compressive forces when the axle moves up, or tensile forces when it moves down. This could lead it to potentially break, buckle, or damage the transmission or differential bearings. The sliding joint ensures the drivetrain can function smoothly and reliably despite the dynamic vertical movements of the suspension system, preventing bind-up.
Right. Okay, we've talked extensively about what makes a car move, how it steers, how power gets delivered. But what about the ride itself? Dealing with the bumps, the dips, ensuring comfort for the passengers, and maintaining overall stability and control, especially on uneven surfaces. That sounds like where the often underappreciated suspension system comes into play. It's handling that constant fight against gravity and road imperfections, isn't it?
Precisely. That's its fundamental role. When a vehicle moves along any road, it inevitably encounters various road shocks and irregularities. These shocks can cause the vehicle body to react in several undesirable ways. It might experience pitching or front-to-back rocking motion, like a boat. It might undergo bouncing a general up and down movement of the whole body. It could involve swaying a side-to-side shift or roll of the body, or rolling a tilting of the vehicle around its longitudinal axis, which is especially noticeable during cornering.
And these aren't just uncomfortable.
No, far from it. These motions not only cause uncomfortable riding for passengers, leading to fatigue and potentially motion sickness, but crucially, they also produce additional stresses and strains in the vehicle's frame or unibody structure and on all the mechanical components attached to it. Over time, these stresses could lead to fatigue failures or damage. To absorb, or ideally prevent, these shocks from reaching the main body and to control the vehicle's movements, a sophisticated two-fold elastic system called the suspension system is used in all modern vehicles.
And you said it's made of two main parts working together to achieve that comfort and stability. It sounds like a clever partnership between components.
Yes, absolutely. A typical suspension system is mainly composed of two primary types of components working in close synergy. The first is an oscillating system, which is usually some form of spring. This could be the traditional leaf spring, or more commonly today, a coil spring, or sometimes a torsion bar, or even an air spring. The spring's job is to absorb the initial impact energy when a wheel hits a bump, allowing the wheel to move upwards relative to the body, thus cushioning the ride.
But springs bounce, right?
Exactly. If you only had springs, the vehicle would continue to bounce uncontrollably for a long time after hitting a bump, which would be very uncomfortable and unsafe. This is where the second crucial component comes in, the damper. This is typically a hydraulic shock absorber.
Okay, the shock absorber.
When the vehicle moves on irregular roads and encounters a bump, the springs immediately compress and then start to oscillate, absorbing the initial impact. However, the damper's job is to quickly restrict the amplitude and duration of these oscillations. It does this by converting the kinetic energy of the spring's movement into heat energy, by forcing hydraulic fluid through small orifices, effectively dissipating the energy and bringing the spring's bouncing motion rapidly under control. This helps the vehicle body settle quickly, maintain stability, and crucially keeps the tires pressed firmly against the road surface for consistent grip and control. The vehicle's chassis or unibody is mounted onto the axles or suspension knuckles through these springs and dampers to provide this vital suspension effect.
So, putting it all together, what does this suspension system mean for us as the person actually experiencing the ride? Why is it so crucial, not just for comfort, but also for safety, and maybe even the longevity of the vehicle itself?
It's paramount for a whole host of reasons, directly impacting your driving experience, your safety, and the vehicle's durability. Firstly, as we've said, it's required for the safety and comfort of passengers. It shields them from the jarring physical effects of road shocks, minimizing fatigue, especially on longer journeys, and simply providing a more pleasant ride.
Oh.
Secondly, it helps to keep the vehicle body on a relatively even keel, maintaining stability when it moves over rough or uneven roads. It's also essential for minimizing excessive body rolling or pitching motions that can occur while turning the vehicle or during heavy braking or acceleration, which prevents motion sickness and, more importantly, helps maintain driver control.
And protecting the car itself.
Yes, it plays a vital role in minimizing the effects of stresses and impacts produced on the vehicle's mechanical components and its structure due to road shocks. It provides a crucial cushioning effect that protects the entire mechanism, engine mounts, exhaust system, body panels from premature wear, fatigue, and damage.
What else?
Furthermore, particularly with independent suspension, it allows for the separate up and down movement of individual wheels. This is key to maintaining the vehicle body in a level position, even when one wheel encounters a significant irregularity like a deep pothole, maximizing tire contact with the road. It also determines and provides the necessary ride height to the vehicle body, ensuring crucial ground clearance over obstacles. And importantly, the suspension geometry is designed to effectively bear and manage the significant torque reactions produced during braking and acceleration, contributing to controlled stopping and starting.
Now, are there different fundamental philosophies behind how suspension systems are designed? Different core approaches to how those springs and dampers interact with the wheels and the body?
Absolutely. Many types of suspension systems exist, each representing different design principles and trade-offs. We have independent suspension, rigid axle or conventional suspension using rubber springs, mixed systems combining elements of independent and rigid, interconnected or linked systems like hydroelastic or hydrogous, and sophisticated air suspension systems. But let's focus on two key ones that represent the most fundamental approaches and clearly illustrate a significant evolution in ride quality and handling capabilities. First, the rigid axle suspension system, sometimes called a dependent suspension. In this setup, a single solid axle beam connects the wheels on opposite sides of the vehicle. The suspension for this solid axle typically uses either one transverse side-to-side leaf spring, or more commonly, two longitudinal front-to-back leaf springs, usually combined with hydraulic shock absorbers mounted between the axle and the frame.
And the steering connection.
With a rigid front axle, the front wheel hubs rotate on bearings mounted on steering spindles. These spindles are attached to steering knuckles, and these knuckle assemblies are hinged or pivoted on the ends of the solid axle beam, allowing the wheels to turn for steering. The pivot point for this hinge is traditionally known as the kingpin, although ball joints might be used in some designs.
That sounds incredibly robust, like it could handle a lot of abuse or heavy loads. But I imagine there's a distinct downside in terms of ride quality given that solid connection between the wheels.
You've hit its main drawback precisely. Its primary demerit is indeed related to ride comfort and handling on uneven surfaces. Because the wheels are rigidly connected by the solid axle, when one wheel encounters a road bump or drops into a pothole, the movement is directly transmitted across that rigid axle to the wheel on the opposite side. This often causes the entire vehicle body mounted on that axle to tilt or lean noticeably.
So a bump on one side affects the whole car.
Yes, essentially. If your left wheel hits a bump, the right wheel is also forced to move upwards to some extent, even if its side of the road is perfectly smooth. This interconnectedness means a disturbance on one side affects the stability and levelness of the whole vehicle body. Consequently, this system is rarely used for the front suspension of modern passenger vehicles today, primarily for reasons of comfort and handling precision. You still find it commonly used for the rear axle of many trucks, some SUVs, and occasionally rear-wheel drive cars, where its simplicity, durability, and high load carrying capacity might be prioritized over ultimate ride refinement. This inherent limitation of the rigid axle leads us directly to the advantages of the independent suspension system. And this is where it gets really interesting for achieving superior ride comfort and handling dynamics, which is what most car buyers want today.
Independent, meaning the wheels act on their own.
Exactly. In an independent suspension system, each of the front wheels, and often the rear wheels too, is mounted and hinged separately to the vehicle's frame or unibody. This means each wheel is completely free to move up and down vertically, responding to road imperfections independently of the wheel on the opposite side of the vehicle.
So if one wheel hits that nasty pothole we talked about, the other wheel on the same axle isn't directly affected, and the vehicle body ideally stays much more level. That sounds significantly more comfortable and stable, especially driving on rough or twisty roads.
That's precisely the benefit. The vertical movement of one wheel, caused by a pit or a bump, does not significantly affect the position or movement of the other wheel on that axle. This allows the vehicle body to remain remarkably level and avoids much of that tilting or leaning motion characteristic of rigid axles. The result is a much smoother, more controlled, and more comfortable ride for the occupants.
What kind of springs does it use?
The system typically uses either a torsion bar spring, a bar that twists, or, more commonly, a helically coiled spring, a coil spring, as its elastic component always paired with a shock absorber to control the motion.
And it can be used front and rear.
Absolutely. This independent suspension philosophy can be employed just on the front wheels, often referred to as independent front suspension or IFS, which is nearly universal in cars today. It can also be used on the rear wheels, known as independent rear suspension or IRS, which is common in many cars, especially those aiming for better handling or ride quality. Or it can even be used on all four wheels, providing the ultimate potential for superior ride comfort, better road holding, keeping the tires in contact with the road, and improved handling stability compared to rigid axle systems, particularly during cornering or on uneven surfaces. It's a key reason why modern cars generally feel so much more refined and capable on a wide variety of road conditions.
Let's get into the specifics of those oscillating components, the springs themselves, because they do the heavy lifting of absorbing impacts. The leaf spring is a real classic, especially in trucks. How does it actually work, and what makes it so suitable for certain types of vehicles?
The leaf spring is indeed a simple yet remarkably effective type of spring. It has been used for centuries, even before automobiles. It's primarily used for suspension in vehicles today, especially in heavy vehicles like trucks, buses, and some SUVs, mainly due to its inherent robustness, simplicity, and immense load-bearing capacity.
How is it constructed?
It's made up of a number of flat strips or leaves of high-quality spring steel. These leaves are typically rectangular in cross-section and are placed one upon another, usually in a graduating manner. This means each successive leaf beneath the top one is slightly shorter than the one directly above it, forming a sort of layered stack.
And they're curved.
Yes, these leaves are preformed into a distinct curvature or camber when unloaded. This curvature is designed so that when the normal working load of the vehicle is applied, the spring deflects and tends to straighten out somewhat, effectively absorbing shocks by flexing. The longest leaf, positioned at the very top of the stack, is called the main leaf or master leaf. Its ends are typically formed into the shape of an eye or loop through which the spring is attached to the vehicle's frame via a shackle or a fixed hanger using bolts.
And the other leaves?
The other, shorter leaves are placed systematically one by one below the master leaf, following its curvature. These leaves are all held together securely as a single unit, usually by a center bolt passing through all the leaves, and also by several clips or straps placed at intervals along the spring's length. These clips prevent the individual leaves from fanning out sideways or shifting relative to each other under load, maintaining the pack's integrity and ensuring they work together effectively.
Okay, and how does this whole leaf spring assembly connect to the vehicle's chassis or frame and the axle? And you mentioned a shackle. What critical role does that play in allowing the suspension to move freely?
Right, the connection is key. The leaf spring assembly is typically clamped rigidly to the axle housing, either front or rear axle depending on the design, usually by means of strong U-bolts that loop around the axle tube and clamp the spring firmly against an axle seat.
Okay, clamp to the axle.
Then the spring itself is pivoted to the vehicle's frame or chassis at its two ends, using the eyes formed on the master leaf. Typically, one end of the master leaf, usually the front end, is attached directly to a fixed hanger bracket on the frame via a bolt and bushing, allowing it to pivot. The other end of the master leaf, usually the rear end, is connected to another hanger bracket on the frame, but not directly. Instead, it's connected via an intermediate link called a shackle.
And the shackle's important because
the shackle is absolutely crucial. Think about what happens when the leaf spring compresses under load when it hits a bump. The spring flattens out, and its overall effective length, measured between the eye centers, actually increases. Conversely, when the load is removed and the spring rebounds, its effective length decreases. The shackle is essentially a short swinging link that accommodates this necessary change in the spring's effective length as it flexes up and down. It allows the spring end to move slightly fore and aft as needed, preventing the spring from binding up or putting immense stress on the frame mounting points. Without the shackle providing this degree of freedom, the leaf spring couldn't compress and rebound smoothly, and the ride would be incredibly harsh and components would likely fail.
Right. And then there are coil springs, which are probably much more familiar visually to many drivers of modern passenger cars. How are they constructed, and how do they differ fundamentally from leaf springs in their application and characteristics?
Coil springs are indeed very common, ubiquitous really, in the suspension systems of lighter and more passenger-focused vehicles. Cars, light trucks, SUVs, primarily due to their compact size, relatively low weight, and excellent ride characteristics, offering a generally smoother and quieter ride than leaf springs.
What are they made of?
They're typically made from a round bar or wire of high-strength spring steel. This circular cross-sectional wire or rod is then carefully heated and wound around a mandrel into a helical or spiral profile, hence why they're also commonly known as helical springs. After winding, they're heat-treated to give them their specific spring properties. Their coiled design allows them to store and release potential energy very efficiently when compressed or extended axially, making them excellent energy absorbers for suspension systems. Now, we can classify coil springs based on how they're designed to handle load, although for suspension, we're almost always talking about compression springs, but broadly. First, you have tension springs. These consist of coils that are wound very tightly together, often touching each other when unloaded. They are specifically designed to resist tensile or pulling apart loads. They usually require a certain amount of initial force just to separate the coils before they begin to stretch significantly. You might find these used in mechanisms like return springs for pedals or maybe in garage door mechanisms, but generally not as primary vehicle suspension springs. Second, and most relevant here, are compression springs. These are the type universally used in vehicle suspension systems. They are wound in such a way that there's a noticeable clearance, or gap, called the pitch, between the adjacent coils when the spring is unloaded. This clearance is specifically required because it allows the spring to deflect axially to compress under compressive loads like supporting the vehicle's weight or absorbing the impact from road irregularities. They get shorter as load increases. Finally, sometimes for very heavy vehicles or for specific packaging reasons, extremely long or strong single coil springs might be needed to adequately handle the loads. However, the physical placement of such very long coils might not be possible within the limited space available under the vehicle frame or within the suspension structure. To cope with the situation, engineers sometimes use a clever arrangement called a compound spring.
Compound, meaning more than one.
Exactly. In a compound spring setup, two or more coil springs, often with different diameters and spring rates, are placed concentrically, one nesting inside the other. This creates a compact yet very robust spring unit capable of handling significant loads or providing variable spring rates while still fitting within the restricted space envelope.
It's truly a fascinating blend of material science, getting the steel just right and clever mechanical engineering to effectively manage the constant dynamic forces imposed by the road surface, all while providing that delicate balance between a comfortable ride and stable handling. The ingenuity packed into these seemingly simple components, from the precise metallurgy of the spring steel to the exact geometry of the coil winding or leaf stacking, is really quite remarkable when you stop to think about it.
It absolutely is. Every single detail, from the alloy composition of the steel to the exact shape and dimensions of the spring, is meticulously engineered and rigorously tested to ensure it performs reliably under continuous, often severe dynamic stress for hundreds of thousands of cycles over the vehicle's lifespan. The journey of these components, tracing the evolution of suspension design from the simple, solid axles and stiff springs of early horse-drawn carriages, right through to today's sophisticated multi-link independent systems with adaptive dampers, really tells a fascinating story of human ingenuity constantly striving for better comfort, improved control, and enhanced safety on the move.
Okay, we've covered a lot of ground on getting a vehicle moving, steering it with precision, keeping it stable, and making the ride comfortable. But arguably, equally important, if not more important from a safety perspective, is the ability to slow it down and stop it effectively when needed. That, of course, is the absolutely crucial job of the brakes.
Yes, brakes are indispensable. They are the devices specifically designed and engineered for the purpose of slowing down and ultimately stopping a moving vehicle. The operation of braking is, in a fundamental physics sense, the direct opposite of accelerating a vehicle.
Opposite how?
Well, when you accelerate, the engine's torque produces a positive traction force at the driving wheels that propels the vehicle forward, increasing its kinetic energy. In the braking operation, the goal is to dissipate that kinetic energy. The brakes achieve this by converting the vehicle's kinetic energy, the energy it possesses due to its motion, into heat energy. This conversion happens through friction generated within the braking mechanism itself. This intense heat is then safely dissipated, mostly into the surrounding atmosphere.
So friction creates heat to stop the car.
Essentially, yes. Applying the brakes creates a braking torque at the brake drums or discs. This braking torque then generates a powerful negative traction force, or braking force, at the peripheries of the wheels where the tires meet the road. This force directly opposes the wheel's rotation, resists the vehicle's motion, and brings it safely to a halt.
So what are the core reasons we absolutely need brakes in any automobile? Beyond just the obvious act of stopping at a red light, what specific functional requirements do they fulfill that are so critical to overall vehicle safety and control?
The requirements for brakes are absolutely paramount for both safety and control, making them arguably the single most critical safety system fitted to any vehicle. Firstly, and most obviously, they are essential to enable the driver to stop the vehicle reliably and predictably, and importantly, in the shortest possible distance, particularly during emergency situations. This ability directly prevents accidents and saves lives.
Absolutely critical.
Secondly, they are vital for maintaining control of the vehicle's speed, especially when descending a steep hill or gradient. Without efficient brakes capable of handling sustained use, a vehicle could easily pick up dangerous, uncontrolled speed going downhill, leading to a potential loss of control.
Right. Engine braking isn't always enough.
Exactly. And thirdly, a secondary braking system, the parking brake or handbrake, is necessary to keep the vehicle securely in a desired position when it's completely at rest on a slope, preventing it from rolling away unintentionally. Which is why using your parking brake is such a simple yet fundamentally important safety habit.
Given their absolutely critical importance, I imagine there must be many different ways brakes can be classified, depending on their specific design, their primary function, and how they're actually activated by the driver or the system.
Yes, there are indeed numerous ways to classify brake systems, reflecting the diverse range of engineering solutions that have been developed to meet this critical function effectively across different types of vehicles and applications. We can classify them on the basis of purpose. Here we distinguish between the main, service, or primary brakes. These are the ones operated by the foot pedal for regular, everyday stopping during driving, and the parking or secondary brakes, usually operated by a hand lever or a separate pedal, designed specifically to hold the vehicle securely when it's parked. Then, on the basis of location, we can have transmission-mounted brakes, which act on the drive shaft or transmission output, often found on some heavy trucks or specialized vehicles. But far more commonly, we have wheel-mounted brakes, where the braking mechanism is situated directly at each wheel hub, allowing for individual wheel braking control, which is essential for stability systems like ABS.
How the driver uses them.
Yes, on the basis of driver's ergonomics, meaning how the driver physically operates them. There are pedal brakes, which are foot-operated, the main service brakes, and hand brakes, or sometimes foot-operated parking brakes, which are typically lever-operated for parking.
What about how they're built?
Right, on the basis of construction. This describes the physical form of the main friction components. The most common types today are drum brakes and disc brakes. Historically, band brakes were also used, particularly on very early vehicles or in some industrial applications.
And how they're powered or activated.
Crucially, on the basis of actuating method, this describes how the braking force is actually applied to the friction components. We have purely mechanical brakes, relying solely on cables and linkages, common for parking brakes. Then hydraulic brakes, which use pressurized brake fluid. This is the most common system in cars and light trucks today. Pneumatic brakes, or air brakes, use compressed air and are standard on heavy trucks, buses, and trains due to the high forces required. Vacuum brakes, using engine vacuum pressure to assist or actuate, were common historically but are less so now. And electric brakes, which use electromagnetic force, are found in some trailer braking systems and are increasingly integrated into the regenerative braking systems of hybrid and electric vehicles.
Assisted braking.
Yes, that leads to classification. On the basis of application of force, we have manual brakes, relying solely on the driver's physical foot force. Then servo brakes, or power-assisted brakes, which use engine vacuum or hydraulic pressure generated by a pump to assist the driver's effort, making the brake pedal feel much lighter and easier to modulate. This is almost universal in modern cars. And power brakes, where the primary source of braking power comes from an external source, like the compressed air system and air brakes, with the driver's pedal mainly acting as a control valve.
And lastly, how the parts move.
Finally, on the basis of action. This describes how the friction elements engage. We have internal expanding brakes, where brake shoes push outwards against the inner surface of a rotating drum. This is the principle of drum brakes. And external contracting brakes, where a band or caliper pads contract inwards onto the outer surface of a rotating drum or disc. This is the principle of disc brakes and older band brakes.
Okay, that's a lot of categories. Let's focus now on the two most common types we see in modern vehicles: drum brakes and disc brakes. Starting with the older design, drum brakes, how are they constructed internally, and how do they actually work to slow down a vehicle when you hit the pedal?
Okay, the drum brake system. At its heart is the brake drum itself. This is a heavy, cylindrical cast iron drum that is mounted concentrically onto the axle hub, meaning it rotates directly with the wheel. Bolted firmly to the stationary part of the axle housing or steering knuckle is a sturdy steel backplate. This backplate serves multiple important functions. It provides a rigid mounting foundation for all the internal brake components, the expander mechanism, the anchor pins, and the brake shoes, and it also acts as a shield, protecting the entire delicate brake assembly from contamination by dust, dirt, water, and road debris.
What's mounted on the back plate?
Mounted pivotally on this backplate are usually two curved brake shoes. These shoes are typically hinged or anchored at one end, the heel end, to fixed posts or pins on the backplate. The other end of the shoes, the toe end, faces towards an expander mechanism. This expander is the component that actually forces the shoes outwards against the drum when the brakes are applied.
What kind of expander?
The expander mechanism can take several forms. In purely mechanical brake systems, like some parking brakes, it might be a rotating cam, a toggle lever linkage, or a wedge assembly. In the far more common hydraulic or pneumatic brake systems, the expander is a wheel cylinder. This cylinder contains one or two pistons that are pushed outwards by hydraulic fluid pressure, or air pressure in air brakes, forcing the brake shoes apart.
And the shoes need to pull back.
Yes. One or more strong retractor springs are connected between the brake shoes or between the shoes and the anchor pins. Their job is to pull the shoes back away from the inner surface of the drum when the brake pedal is released, ensuring the brakes don't drag and overheat when not needed.
And the friction material.
Crucially, friction linings made of highly durable, heat-resistant composite materials are riveted or bonded onto the outer curved surface of the brake shoes. These are the materials that actually make contact with the rotating drum to generate the braking friction. Finally, an adjuster mechanism is usually incorporated, often near the anchor pins. Its purpose is to automatically or manually compensate for the gradual wear of these friction linings over time, maintaining a consistent small gap between the shoes and the drum when the brakes are off, ensuring consistent pedal feel and braking performance throughout the life of the linings.
Okay, that's the construction. Now the working mechanism. How does pressing the pedal translate into stopping power with this whole drum brake assembly?
Right. When the driver decides to stop or slow down the vehicle, they exert a nominal force by pressing the brake pedal. This initial, relatively small force exerted by the driver's foot on the brake pedal is then significantly multiplied, first mechanically by the pedal linkage ratio, and then hydraulically by the master cylinder pushing fluid into the smaller wheel cylinders, or pneumatically in air brake systems.
Okay, force gets multiplied.
This highly amplified force, now in the form of hydraulic pressure, acts on the pistons within the wheel cylinder expander. These pistons push outwards, forcing the brake shoes to pivot outwards on their anchor pins and press firmly against the inner surface of the revolving brake drum.
Shoes hit the drum.
As the brake shoes, with their friction linings, expand and make forceful contact with the rotating drum, they generate immense friction. This friction creates a powerful braking force, or torque, acting on the drum, which directly resists its motion and causes it to slow down rapidly. Since the drum is rigidly connected to the wheel hub, the wheel also slows down, and consequently the vehicle decelerates and eventually stops. Drum brakes can be quite powerful, especially designs that use a self-servo or self-energizing effect, where the rotation of the drum actually helps to wedge one of the shoes even harder against the drum, further increasing braking force.
But they have downsides.
Yes. Their main downside is heat dissipation. Because the mechanism is enclosed within the drum, heat generated during heavy or prolonged braking can get trapped. This can lead to the drum expanding, the friction material overheating, and a reduction in friction coefficient, a phenomenon known as brake fade, where braking effectiveness diminishes significantly. They can also be more prone to grabbing or locking up unevenly compared to disc brakes and are generally more complex to service.
Which leads us nicely to disc brakes. Nowadays, these are far more common, especially on the front wheels of almost all passenger cars, and often on the rear, too, particularly in performance vehicles or heavier SUVs. What makes them fundamentally different in design from drum brakes, and how do they achieve what's generally considered superior stopping power and better heat management?
Disc brakes represent a significant evolution and improvement in braking technology, largely developed to overcome the inherent limitations, particularly the heat dissipation issues, of traditional drum brakes. The fundamental difference is right there in the name. In disc brakes, the heavy enclosed cast iron drum is completely replaced by a flat circular plate called a disc or rotor. This disc is mounted rigidly to the wheel hub and rotates along with the wheel, but it's open to the air.
Okay, so a disc instead of a drum. What replaces the shoes?
The brake shoes, which push outwards inside a drum, are replaced by a component called a caliper. The caliper is a C-shaped or bracket-like assembly that straddles the edge of the rotating disc. Instead of shoes, the caliper holds and supports a pair of flat friction pads, one positioned on each side of the disc, ready to clamp down onto its surfaces.
So pads squeeze the disc.
Exactly. When an operating force is applied to these pads, usually via hydraulic pistons housed within the caliper, they are forced inwards, clamping down powerfully onto both sides of the spinning disc. This generates intense friction between the pads and the disc surfaces, creating the braking torque that retards the disc's rotation and stops the wheel. The means of actuation for the caliper pistons can vary. It could theoretically be mechanical or even electromagnetic in some specialized cases, but hydraulic actuation using brake fluid pressure is by far the most common and effective method used in passenger vehicles and motorcycles.
So the caliper is really the key active component here. It contains all the moving parts that do the actual stopping work.
Yes, the caliper assembly is absolutely central to the functioning of the disc brake system. A typical caliper-type disc brake essentially consists of the rotating disc itself and those two friction pads, one on the inboard side and one on the outboard side. These friction pads are actuated most commonly by one or more hydraulic pistons, sometimes just one in a floating caliper design, sometimes 2 or 4 or even 6 in a fixed caliper design for high performance. These pistons are housed within precision bored cylinders machined directly into the body of the caliper assembly.
And the caliper is fixed.
The caliper assembly itself is rigidly attached, either directly or via a mounting bracket, to a stationary part of the suspension, typically the steering knuckle for front wheel brakes or the axle housing or trailing arm for rear wheel brakes. This ensures the caliper stays stationary relative to the vehicle body while the disc rotates past it. The friction pads are designed to slide slightly within the caliper structure so they can move inwards to contact the disc when the brakes are applied and retract slightly when released, maintaining just a minimal clearance to avoid drag.
How are the pistons activated?
One or more hydraulic wheel cylinders are effectively integrated directly into the caliper casting. These cylinders are connected via internal passages and external brake hoses or lines back to the main hydraulic brake lines coming from the master cylinder, allowing pressurized brake fluid to reach the pistons and activate them.
Okay. And so how does this sophisticated system actually stop the car? Trace it from the driver's pedal input right through to the wheels halting, and what fundamentally makes it so effective, especially compared to a drum brake in demanding situations.
Right, let's follow the sequence. When the brakes are applied by the driver pressing the pedal, brake fluid, which is usually a specialized, non-compressible glycol-based fluid, is pressurized by the master cylinder system. This high-pressure fluid is then pumped through the brake lines and hoses and enters the caliper assembly, typically through an inlet port or banjo bolt connection.
Fluid enters the caliper.
Upon entering the caliper, the pressurized fluid flows through a network of internal passages drilled within the caliper body. As it flows, it exerts equal pressure on the back of the hydraulic piston housed within the caliper's cylinders.
Pistons move.
These pistons, under the significant hydraulic pressure, are forced outwards from their cylinders. As they move outwards, they push the attached friction pads inwards, forcing them to apply a powerful, even clamping force against both rotating surfaces of the brake disc.
The pads clamp the disc.
This immense clamping pressure generates very high friction between the stationary pads and the moving disc surfaces. This friction resists the disc's rotation, thereby stopping the axle shaft and the wheel connected to it from turning, bringing the vehicle to a controlled halt. When the driver releases the brake pedal, the pressure in the hydraulic system drops. Retraction mechanisms like square-cut seals around the pistons or sometimes small springs help to pull the pistons back slightly into their bores, releasing the clamping pressure from the friction pads and allowing the wheel to rotate freely again with minimal drag. Now, the key advantage, especially compared to drum brakes, lies in heat dissipation. Because the disc rotor itself is largely exposed to the surrounding airflow, the significant heat generated by friction during braking can dissipate much more rapidly and effectively into the atmosphere. Many discs are also internally ventilated with radial vanes to further enhance this cooling effect.
So less chance of overheating.
Far less chance. This means disc brakes are significantly less prone to suffering from brake fade, the dangerous reduction in braking power due to overheating, especially during repeated hard braking, high-speed stops, or long downhill descents where brakes are used continuously. This makes them inherently safer and provides much more consistent, predictable braking performance under a wide range of demanding conditions. They also tend to perform better in wet conditions as water is flung off the disc surface more easily, and they are generally simpler to inspect and service than enclosed drum brakes. This overall superiority in performance and consistency, particularly regarding heat management, is why disc brakes have become the standard, certainly for front wheels, and increasingly for all four wheels in modern passenger vehicles. And, considering the complexity and the continuous refinement we see in these braking systems, things like ABS, stability control, regenerative braking in EVs, all building upon these fundamentals, it really raises an important question for the future. How much more innovation can there possibly be in the automotive world? Especially as we move deeper into the era of electric powertrains and increasingly sophisticated autonomous driving systems, where braking control becomes even more critical and often electronically managed. It's a space that's constantly evolving. Hashtag tag shag outro.
Wow. So what does this all mean at the end of the day? We've journeyed today from the very first spark of an internal combustion engine, understanding how that raw power is harnessed and controlled, right through to the intricate precision of a modern braking system, meticulously designed for our safety and control. It's really revealed the incredible depth of design and sophisticated engineering that goes into every single vehicle we interact with, often without a second thought.
It really is something, isn't it? It's like a complex ballet of physics and mechanics, all these disparate systems, engine, transmission, steering, suspension, brakes working seamlessly and usually invisibly together, all orchestrated just to get you safely, comfortably, and efficiently from one place to another. And if we try to connect this foundational knowledge to the bigger picture, understanding these core engineering fundamentals doesn't just deepen our appreciation for these remarkable machines we rely on daily. It also empowers us as drivers or just as informed citizens to think more critically and knowledgeably about the new automotive technologies that are emerging so rapidly now, things like electric vehicles and increasingly sophisticated autonomous driving systems.
How so?
Well, while the power sources and the control systems themselves may evolve dramatically, for instance, electric vehicles don't need complex multi-speed gearboxes in quite the same way, though they still often need reduction gears and differentials. Many of the core mechanical principles we've discussed remain absolutely foundational. Things like the necessity of robust, well-damped suspension for comfort and road holding, or the importance of precise steering geometry for directional stability and driver feedback, or the fundamental physics of friction braking. These principles don't just disappear.
They're just adapted.
Exactly. They're simply reimagined, refined, or perhaps actuated and controlled in new ways, often electronically rather than purely mechanically. It really proves that fundamental engineering principles are quite timeless, even as their specific applications change and adapt to new technologies and societal needs. The challenges remain, the solutions evolve.
That's a great point. It truly highlights that even the most common everyday objects around us, like our cars, are absolutely packed with ingenuity, layer upon layer of careful thought and refined design that we often just take completely for granted. Our hope today with this deep dive is that we've given you, our listeners, perhaps a shortcut to being a little more well-informed about the incredible, intricate world of automobile engineering, and maybe, just maybe, given you a new level of appreciation the next time you get behind the wheel or even just ride as a passenger.
We certainly hope so, and we'd encourage you to continue your own learning journey if this has sparked your interest. This deep dive, as comprehensive as we've tried to be, has really only scratched the surface of the vast and fascinating knowledge available within the field of automotive engineering, a field that continues to evolve at an astonishing pace. There is always so much more to explore through resources like Knowledge Flow.
You've been listening to The Deep Dive, presented by Knowledge Flow. Thank you for joining us. We can't wait to unpack another fascinating topic with you next time.